Hey friends, Dr. Borole is here. Today we are going to start the discussion on unit number 3, the number system and logic gates. As per your university syllabus, the following topics are mentioned in the syllabus. Under number system, the binary number system, BCD, octal, decimal, hexadecimal number system, and their conversion and arithmetic in this number system is to be discussed. The theorem, those are used in binary number systems called De Morgan's theorem, those are covered. Then our focus will be changed to digital electronic building blocks. Those are basic gates, AND gate, OR gate, NOT gates. Then we will study universal gate. Those are NAND gate and NOR gate. Then we will see some of the building blocks using basic gates and implementation like half adder and full adder. Then we will see the memory storage element like flip-flops. Under flip-flop, we will see SR flip-flop, JK flip-flop, T flip-flop, and D flip-flop, that data flip-flop. The last topic will be introduction to microprocessor and microcontroller. And here it is mentioned only block diagram and explanation. That is your syllabus of unit number 3. So let us start. We will start with some preliminaries. Let us see signals and systems. In electrical engineering, we will mostly focus on two signals, that is voltage and current. According to their representation, the signals are classified under two categories, analog signals and digital signals. The voltage and current signals are the functions of time. The analog signals, also called as continuous time signal, they are the function of t, like if it is a voltage, it is a function of t, and it will be represented by infinite set of points. Means they plot a continuous trace of line. They can be repetitive or non-repetitive. The digital signals are also called as discrete time signals, and they are represented by only finite set of points. Means they are defined at particular time only. Following figure shows the examples of digital signals and analog signals. See here in the figure 1, here it is a sinusoidal signal and it is a continuous time signal. And you will see that it traces a smooth line with respect to time. Means for every instance of time, there is corresponding value of the voltage. So this signal will be represented by infinite number of points, and that's why it is continuous signal. The analog signal and digital signal can be repetitive or non-repetitive. Here in this figure, the sinusoidal signal is repetitive and it repeats with a specific time period. Whereas if you see the digital signal have only discrete values. For example, for certain duration, the value is 5 volt. Then the next duration it is 0. Again for the next interval, it is 5 volt. Again it is 0 volt for the next duration. Likewise. So total signal is repetitive, but it will be only represented by the discrete values. In the second figure, you will see again another type of analog signal. Again, analog signal need not be having constant amplitude. It can have any amplitude, only it will be represented by infinite number of points. So for every time instant, there is a corresponding value of the signal. This type of signals are called as analog signal. If you see the corresponding digital signal, the digital signal will be only defined by the few discrete values. For example, during this interval, first interval, the digital value is shown here. Whereas during second interval, the digital value is low, right? Whereas during the third interval, the digital value is change again. Likewise, only few values represents the digital signal. If you compare these two signals, their variations are similar, but here compared to analog signal, digital signal have many lost part. Some of the parts of the analog signals are lost while converting it to digital signal. The third figure again indicates another analog signal which is randomly vary with respect to time, but it is continuous signal. Whereas the digital signal shown here, which is having only two values, the high value and low value. By using only two values, the signal can be represented in this particular example. So by conclusion, we can say that analog signals are the set of infinite point signal, whereas digital signals are represented by a finite set of points. The digital signal representation. The type of digital signal can be represented by binary combinations. Number of distinct values are shown here. In binary, there are only two distinct values, 0 and 1. If the signal is represented by octal system, then there are number of distinct values are 8. If it is represented by hexadecimal system, then the number of distinct combinations are 16. Now let us see what is system or circuit. System is basically a group of interconnected component or physical devices or algorithm to perform the required operation on the applied input data or signal. There are two types of system generally classified in theory: analog circuits and digital circuits, or say analog systems and digital systems. The analog systems are the system which process the analog signals. They are having input as analog signals and the processed output, that is also the analog signal. The typical examples are filters, amplifiers and signal generators, etc. The digital systems are also called discrete system. These system process the digital signal to produce the digital signal output. See in the block diagram, this is the digital system or circuit. Inputs are digital inputs. It can be single channel or multi-channel digital inputs or multiple digital signals, and it can generate single or multiple output digital signals. The typical examples are digital adders, subtractors, the data registers, the flip-flops, the counters, microprocessors, calculators, and computers, and so on. The binary logic and logic levels. In binary systems, there are two systems of logic representation: the positive logic system and negative logic system. In positive logic system, there are two symbols, logic 0 and logic 1. Logic 1 corresponds to true, that is in electrical circuit represented by 5 volt, and logic 0 that corresponds to false, and that is represented in actual electrical circuit by 0 volt. Whereas in negative logic system, the role of true and false will be reversed. The true means it is logic 1, and that is represented by 0 volt in the electric circuit, and false is logic 0, and that is represented by 5 volt in the corresponding binary electric circuit. It is shown in the figure here. See, in the negative logic system, 0 volt level is logic 1 here, and in positive logic system, 0 volt corresponds to logic 0. Whereas in positive logic system, 5 volt corresponds to logic 1, whereas in negative logic system, 5 volt corresponds to logic 0. Most of the time, we are using positive logic system only. Let us focus on the study of number systems. Number system have two important components: the base of the number system, also called radix, and the weight of the system, that is also called as positional weight. The base of the system is nothing but the number of symbols used to represent the various positions of digit in the system. For example, in digital system, the number of symbols used are 0 to 9. Therefore, total number of symbols are 10, and thus the base of the system is 10. The largest digit in the decimal system is base minus 1, that is 10 minus 1. And this logic is applied to all forthcoming system. What is weight? Weight is basically a positional value of the digit. Let us see the example here. If this is a system, there is a point called radix point. Left hand side to the radix point is a integer portion, and to the right side of the radix point there is a fractional portion. So let us see the position here. Let us consider the position is numbered from 0. So 0th position is immediately to the left of the radix point, then first position, then second position, then third position, and so on. The position weight shown here is b raised to power 0. B stands for base of the system. B raised to power 1, B raised to power 2, and so on, increasing towards the left. For example, if base of the system is 10, means it is decimal system, then 0 position is 10 raised to 0. We are calling it unit position. The first position is b raised to 1, that is 10 raised to 1, means 10. The weight of first position is 10. Weight of second position is 10 raised to 2. Weight of third position is 10 raised to 3. And weight of fourth position is 10 raised to 4, and so on. That is in decimal system. So here the figure indicates a generalized diagram of any number system in which the integer part is the left part of the radix point, and the positions are from 0 position to n number of position. Those are increasing in left side, and the position weight will be the power of the base starting from 0. So the power go on increasing from 0 to n on left side for integer portion. If you see the fractional part, the right side of the radix point, then the position weight of the first position is given by b raised to minus 1, where b is the base again. Second position will be b raised to minus 2. Third position will be b raised to minus 3 and so on. For example, if it is a decimal system, then base will be 10. So this first position will be 10 raised to minus 1 means zero point 0.1. Second position will be 10 raised to minus 2 means 0.01. Third position weight will be 10 raised to minus 3 means 0.001 and so on. Let us see the example in the decimal system. If the number is 349.25, how it can be represented by the system? Whereas if you see the number representation here, the number will be put in the bracket and there is a subscript 10 mentioned. This is one way to represent that this number is a decimal system. Whereas in decimal system, we normally ignore this subscript. Sometimes instead of 10, the letter D can also be used. And in decimal system representation, most of the time, we simply ignore the subscript. We just say 349.25 is a decimal number. Now, if you see this number and its corresponding weight, see the integer portion left to the decimal point. Now, this radix point becomes the decimal point. The zeroth position is 9, that is unit position. So, it will be, the digit will be multiplied by the weight of the position, that is 10 raised to 0. So, that corresponding total weight of this first position is 9 plus into 1, that is 9. The second digit is 4 and weight of the position is 10 raised to 1. So, therefore, the total weight of second position or this position is 4 into 10 raised to 1, that is 40. If you see the third digit is 3 and the position weight is 10 raised to power 2. So, therefore, that is 100. So, 3 into 100 is 300. So, therefore, position of or total weight of this digit 3 is 300. Add these all the weights, 300 plus 40 plus 9, that becomes 349. Whereas if you see the fractional portion, in the fractional portion we know the position weight is increasing with the negative power of base. Here base is 10. So the first digit after the decimal point on right hand side is 2. The positional value of this position is 10 raised to minus 1. So therefore, the value will be 2 by 10, that is 0.2. Whereas the next digit 5, the position value is 10 raised to power minus 2, that is 5 by 100 means 0.05. And therefore, the total value will be addition of these individual position weights and that comes out to be 0.25. This general fundamental will be applicable to any system further we are going to study. So if you remember this, you can easily understood the forthcoming systems. The various number systems, those are used in practice, are listed here with their base values. The binary systems have base value 2, means there are only two symbols to represent any number in binary. The octal number system have the base value of 8. The decimal number system have the base value of 10. The duodecimal system have the base value of 12. The hexadecimal system have the base value of 16. Means in hexadecimal system, the total number of symbol used to represent any number is 16. Out of this system, binary system, decimal system and hexadecimal systems are quite popular. Let us review the decimal systems to which we are very familiar. The system base is 10, means number of digits used are 0 to 9. The largest value of any digit will be 9. The position weight is multiple of power 10 as shown here. Let us see the radix point. The integer portion, we will see the zeroth position, the position weight is 10 raised to 0, that is 1. The first position, the weight is 10 raised to 1. The second position, the weight is 10 raised to 2. The third position, the weight is 10 raised to 3, and so on. On the right side of the decimal point, it is the fractional portion. The first position have weight 10 raised to minus 1. The second position have weight 10 raised to minus 2. Third position have weight 10 raised to minus 3, and so on. Let us see the another number system, the binary number system. In binary number system, the system base is 2. Means there are only 2 digits to represent any number, 0 and 1. We can say logic 0 and logic 1. The largest value of the digit is logic 1. The position weight is the multiple of power of 2. Again, see the radix point. Here, radix point is now the binary point. The zeroth position have the positional weight of 2 raised to 0. The first position have the positional weight of 2 raised to 1. The third position have, second position have the positional weight of 2 raised to 2, and so on. On the right side of the binary point, the first position have the weight of 2 raised to minus 1. Second position have weight 2 raised to minus 2, and so on. A typical example is shown here. Let us find out the equivalent decimal number corresponds to the binary number 1011.011. Whereas here the number in red is the integer portion and the number in blue color is a fractional part. So the binary value is written as it is here in the figure. Consider the binary point. The left side of the binary point is the integer portion. The zeroth position have the weight 2 raised to 0. So the digit is 1 into 2 raised to 0. The positional value is therefore 1 into 2 raised to 0 is 1. The first position is 1 into 2 raised to 1. Therefore, the weight of this position digit is 2. Third digit is 0. So 0 into 2 raised to 2. And therefore, the total position value of this digit is 0. The third position digit is 1 and therefore the weight is 2 raised to 3. So 1 into 2 raised to 3, that is 8. So we have individual positional weight 8021. Add the all position weights. You are getting the total integer portion. That is 8 plus 2, 10 plus 1, 11. So integer value will be 11 as shown here. Now let us convert the fractional portion. We know the first position to the right of the binary point, the position weight is 2 raised to minus 1. So 0 into 2 raised to minus 1 is 0. The second position is here shown by the digit logic 1. So 1 into 2 raised to power minus 2, that comes out to be 0.25. The third position is the least significant position. The digit is 1. So 1 into 2 raised to power minus 3, that comes out to be 0.125. Add all the individual position weights of the digit. So 011 binary corresponds to 3.75 decimal. So total number, therefore 1011.011 in binary is corresponds to 11.375 in decimal. The binary numbers are represented in number of bits format. Here, bit defines the single position, whereas nibble defines the combination of 4 bits. Byte defines the combination of 8 bits, and word defines the combination of 16 bits. Likewise, double word defines 32-bit and quad word defines the 62-bit representation of a binary number. A table here typically shows the representation. If you see the word representation, the binary value represented here by 16-bit, whereas in nibble, each binary value will be represented by group of 4 bits. In bytes, each binary value will be represented by group of 8 bits. Let us see the another number system, octal number system. The name itself indicates that this system have base 8. Means this system have the total number of symbols 8, that is 0 to 7 digits. The largest value of the digit is 7. The position weight is the multiple of power of 8 as shown in the figure. So see the integer portion. The same logic we will apply here. The radix point is now called octal point. The 0th position have the weight 8 raised to 0, that is 8 raised to power 0. The first digit have the weight 8 raised to power 1, that is the position number. The second position have the weight 8 raised to 2, and third position have the weight 8 raised to 3, and so on. The fractional portion, that is to right of the octal point, the first position have the position weight of 8 raised to minus 1, that is actually 1 by 8. The second position have the positional value 8 raised to minus 2, and the third position have the power 8 raised to minus 3. The typical number system shown in the table here, it consists of only 7 digits, 0 to 7 digits, means 8 symbols. So the numbers are 0, 1, 2, 3, 4, 5, 6, 7. And after 7, the next digit will be 1, 0, then 1, 1, 1, 2, up to 1, 7. After 1, 7, the significant digit will be increased by 1, and least significant digit, the lowest digit, will be reset to 0. So therefore, the next column, you will get the number 20 to 27. The third column, after 7 of least significant position, made 0, and the most significant position of the column will be incremented by 1, that is 3. So 30 to 37. From 37, it will be 40 to 47, and so on. In decimal system, if you compare this, we are going from 0 to 9. After 9, it will be 10 to 19. Then after 19, it will be 20 to 29, and so on. So in every system, the logic is same. You have to only identify what is the base of the system, and then accordingly find out the weight of the position, that is power of the base, and the total number size can be obtained by adding each positional weight, integer portion as well as decimal portion, and that represents the number in that system. Let us see the another system, hexadecimal system. Now hexadecimal system have the base of 16. The digits used to represent the hexadecimal digits are 0 to 9 and A to F. So total number of digits are 16. The largest value of the digit is F. The position weight is therefore multiple of power of 16. As shown in the example, here the digits are shown 0 to F and their corresponding value is 0 to 15 in decimal, whereas the representation in hexadecimal is 0 to 9. After that, A, B, C, D, E, F. These are the hexadecimal representation and corresponding decimal notation will be shown here as 0 to 15. A typical number system now shown by the same diagram again. The radix point is now called hex point. The left side of the hex point is the integer portion and right side of the hex point is the fractional part. The leftmost digit is called MSD, most significant digit, and the rightmost digit is called as least significant digit. Now, if you see the position 0, that is the first position of the integer portion after the radix point on left hand side is 16 to power 0 because base of the system is 16. The first position have the position value 16 raised to 1. The second position have the position value 16 raised to 2 and so on. To the right side of the radix point, that is the fractional portion, the weight of the first position is 16 raised to minus 1. Second position is 16 raised to minus 2. Third position is 16 raised to minus 3 and so on. A typical number system shown in the table, the digits are increasing from 0, 1, 2, 3, 4 up to F, and after F, the MS digit will be incremented and lower digit will be resetted. So here if you see, the MS digit is 1 and lower digit will be resetted as 0. So again 1, 0, 1, 1, 1, 2 up to 1 F. When the last digit becomes F again, the MS digit is again incremented, that is 2, and LS digit will be resetted to 0. And again LS digit is changing from 0 to F. Again same thing is repeated in the fourth column. The MS digit will be incremented to 3 and LS digit will be resetted. So we will see the hexadecimal table continues to multiple digits values. Here only 2-digit hexadecimal representation is shown in the table. Now let us see the conversion of the number system. Any number system to decimal number system that can be achieved by summing all positional values into position wise weights. Now position values are the digit values given at that position and position weight is basically the weight of the system at that position. Take an example, binary to decimal conversion. The number given in binary, which is shown here 1011.01. We have shown the subscript 2 here, which indicates that it is a binary number. That is the way to represent the binary number. In many literature, this will be dropped. But the right convention is to add a suffix 2 to represent the binary number, which we want to convert to equivalent decimal number. So we have written the binary value here 1011, then binary point and 01. This is the input value given to us. We need to convert it to the decimal equivalent. We know the weight of the binary system or base of the binary system, that is 2. So position 0 have the weight 2 raised to 0. Position 1 have the weight 2 raised to 1. Position 2 have the weight 2 raised to 2. position 3 have the weight 2 raised to 3 and so on to the left side of the binary point. That is the integer portion. So therefore, here at 0th position in the integer section, we will see the total weight of this 0th position is 1 into 2 raised to 0. That is 1. The first position, the binary bit is 1 and the weight is 2 raised to 1. So therefore, the weight of this binary digit is 2. Third position, the binary digit is 0, weight is 2 raised to 2. So 0 into 2 raised to 2 is 0. The third bit, that is the most significant bit, MSB or MSD you can call it, 1 into position is 2 raised to 3, 2 raised to 3 is 8. So therefore, the weight of this 1 in MSD position is 8. Add the total individual position weights. 8 plus 0 plus 2, that is 10 plus 1, that is 11. So total binary integer portion have the decimal value 11. Now consider the binary value. Right side to the binary point. That is the fractional portion. The first position here have the weight 2 raised to minus 1 and the digit here is 0 into 2 raised to minus 1, that is 0. Here there is a typo mistake. Let us correct it. Okay, I have corrected it. So the first position have the position weight 2 raised to minus 1. So 0 into 2 raised to minus 1 is 0. The second position digit is 1. 1 into 2 raised to minus 2 is 0.25. So 0 plus 0.25 is 0.25. So therefore, the number 1011.01 binary is corresponds to 11.25. Let us see the example of octal to decimal conversion. Let us see the number given is octal number 358 and 8 here as a subscript, that is indicating the octal number. So 354 octal into decimal conversion. So we have written the number 354, that is in octal. The position values as usual, only integer portion is given here. The 0th position is this last digit 4. 4 into 8 raised to 0, that is 4. Second, the first position is 5. 5 into 8 raised to 1 is 40. The second position digit is 3. 3 into 8 raised to 2 is 192. And therefore corresponding value, add all these three values, that is 236 decimal. So 354 in octal corresponds to 236 decimal. Let us have another example, octal into corresponding decimal number with a fractional value also. So 365.25 octal is converted to corresponding decimal number. So let us see the octal point now. The 0th position is 5. 5 into 8 raised to 0, that is 5. First position is 6. 6 into 8 raised to 1, that is 48. The second position is 3. 3 into 8 raised to 2, that is 192. So decimal portion as usual 192 plus 48 plus 5, that comes out to be 245 here. Now to the right side, the fractional portion. The first position is 2. 2 into 8 raised to minus 1. 8 raised to minus 1 is the positional weight. And therefore, the first position digit weight is 0.25. Whereas the second position digit is 4. 4 into position weight is 8 raised to minus 2. And that comes out to be 0.03125. Add the 2. So therefore, you are getting the value that is equal to 0.28125. So 365.24 octal corresponds to 245.28125 decimal. Let us see hexadecimal to decimal conversion. On the same track, we have 4C8.2 hexadecimal into equivalent decimal number. We have written now here the hex value. The hexadecimal point is also shown. Now the zeroth position is the digit 8. Corresponding positional weight is 16 raised to 0. So 8 into 16 raised to 0, that is 8. The second position digit is C. The corresponding decimal value is 12. So 12 into 16 raised to 1, that is the positional weight. So it comes out to be 192. The third digit is 4. So 4 into the positional value, that is second position, 16 raised to 2, that is 1024. Add these three individual positional weights, you are getting the integer portion of hexadecimal value corresponds to or corresponding decimal value of this hexadecimal integer, that is 1224. Now let us see the fractional portion. The first position is digit is 2, the weight is 16 raised to minus 1. So therefore this comes out to be 2 into 16 raised to minus 1 is 0.0125. The second digit is 4 into 16 raised to minus 2. So therefore the positional value, digit value is 0.015625. Add the 2, you are getting the fractional portion in the decimal. So therefore here the last column indicates the hexadecimal value and corresponding decimal value. You also note here that the subscript H is shown here, that is indicating the hexadecimal digit, and D indicate the decimal digit. So instead of 10, D can also be used. Now conversion from decimal system to binary system or octal system or hex system. The decimal to binary conversion is also known as double-double method of conversion. The decimal to hexadecimal conversion is also known as hex-double method of conversion. In these methods, we are converting the integer portion and fractional portion separately and then attaching. Let us see what is the double-double method. In double-double method, let us say decimal to binary conversion, we will continuously divide the number by base and note the remainder and list the remainder values in reverse order, that is from bottom to top. Let us see the example. Here the number given is 105 decimal and we want to convert it to binary. So base of the binary system is 2. So we will continuously divide this number by 2. First time divide by 2. So you are getting quotient 52 and remainder 1. Then divide this 52 by again 2. You are getting quotient 26. Remainder 0. Then this 26 will be divided by 2 again. You are getting quotient 13. Remainder 0. Then 13 will be divided by 2. You are getting quotient 6. Remainder 1. Then 6 will be divided by 2 again. Quotient will be 3. Remainder will be 0. 3 will be divided by 2. Quotient will be 1. Remainder will be 1. Again 1 will be divided by 2. You will see the quotient will be 0 and remainder will be 1. After this, when the digit reaches to 0, we have to stop the division. Once this division is complete, go on writing the binary reminders from bottom to top, as bottom digit or bottom reminder is MSB and top reminder is LSB. So therefore, 105 decimal will be converted to 11010001 binary as shown here. So what we have done? We have taken the number, continuously divide it by 2 and note the remainder. The first remainder will be LSB and the last remainder will be MSB. And the division process will be automatically stopped when quotient becomes 0. On the similar track, if you want to convert decimal number to octal number, now what is the base of octal system? That is 8. The number given is 204 decimal. Now we are going to divide it by 8. So 204 divided by 8. The quotient is 25, remainder will be 4. Again 25 will be divided by 8. Quotient will be 3, remainder will be 1. Then 3 will be divided by 8. Quotient will be 0, remainder will be 3. After this, the process will stop because 0 divided by 8 again, that is the base of the system, will 0 itself. And therefore, we got the end of the conversion process. After this, whatever the last reminder we are getting, that is most significant digit, and the first reminder will be least significant digit. So we are writing the reminders from bottom to top. Bottom will be MSD and first reminder will be LS digit. Similarly, decimal to hexadecimal conversion. Here again in this method, we will see the number given is 259. Our method is we are dividing it by 16. The base of the hexadecimal system is 16. So 259 by 16. The quotient will be 16 and remainder will be 3. Then this 16 will be divided by again 16. The quotient will be 1 and remainder will be 0. Again 1 will be divided by 16. Quotient will be 0 and remainder will be 1. Now write the reminders from bottom to top as MSD to LSD. So 103 will be corresponding hexadecimal number, corresponds to the decimal number of 259. By using this logic, we can convert the various numbers and tabulated some basic combinations in the table shown here. So you will see, first column indicates the decimal numbers, second hexadecimal number, corresponding binary number in the third column, corresponding octal number is shown in the fourth column, and the binary combination corresponds to this octal number is shown. Decimal 0 corresponds to hex 0. Up to 9, the hex number and decimal numbers are same. In decimal number, after 9, it will be incremented to 10. Whereas hexadecimal number have total 16 symbols. So next symbol will be A, then B, then C, then D, then E and F. So therefore F corresponds to 15 decimal. The corresponding binary value will be from 000, 1 will be 001, 2 will be 010, 3 will be 0010, 4 will be 100, 5 will be 0101, 6 will be 0110, 7 will be 0111, 8 will be 1000, and 9 will be 1001. 10 will be 1010 and so on. So F will be 1111. Corresponding octal number, up to 7 the numbers are same. After 7, the last digit will be resetted and next digit will be 1. So 8 corresponds to 10 in octal, 9 corresponds to 11, 10 decimal corresponds to 12 and 15 corresponds to 17 octal. The octal number is normally have only 7 digits and to represent the 7 combination in binary, only 3 binary digits are required. So 0 corresponds to 000 and 7 corresponds to 111. The next digit octal representation in binary form is 001 000, that is 10. 10 is the first octal number is represented by 3-bit binary, and second octal combination will be represented by next 3 bit. So 10 in octal will be represented by 6 digits in binary. So likewise, the digit 17 in octal will be represented as 001, corresponds to this MSD, and 7 LSD will be represented as 111. These combinations, decimal, hexadecimal and binary, you need to remember because these are required many number of times further in the subjects of digital electronics. Now let us see the fractional part conversion to binary. In this process, what we will do is, instead of division, we will use the successive multiplication of the fractional part. Multiply only fractional parts successively by base and note down the carries. Let us see the example. Now decimal fraction to binary fractional number can be converted like this as shown in the figure. Let us convert the decimal number 0.42 into binary. So what is our logic? We will take a fractional portion given, that is 0.42. The base of the binary system is 2. So 0.42 into 2, 0.84. Here no carry is generated. See, carry is 0 and therefore it is noted as 0. Take the fractional portion again, 0.84 multiplied by 2. Here after multiplication we are getting the product 1.68. So carry is 1 and fractional portion is 0.68. So fractional portion will be continued in the successive multiplication and corresponding carry will be noted down. So similarly, this process will be continuously going on. And once the process stops, we will note the carry. The last carry will be considered as the LSB and the first carry generated will be MSB. Here, this process shown in 5 steps, but 6 step is also present, 0.44 into 2 again. Then whatever the remainder, again you can go on multiplying by 2. But ultimately, the last carry will be always LSB, and LSB values are very least significant, and therefore after decimal point the rightmost value, that is LSB value, will be ignored and truncated up to significant digits only. So here we will truncate this value up to 5 binary significant digits and we will stop the process up after 5 steps. So therefore 0.42 decimal portion, this is the fractional part, is corresponds to the binary fraction 0.01101. Let us take another example. Convert the number 0.6234 to XXX8 shown here. So indirectly they are asking us to convert this fractional portion to octal number fraction. Again the process is same. We have to successively multiply by the base of the system in which you want to convert. We want to convert in octal and therefore base of the system is 8. Take the fractional portion again, whatever given, that is 0.6234 multiplied by 8, you are getting the product. From the product, the carry portion is taken out and fractional portion remains as it is. The fractional portion is in the next step taken and multiplied by 8 again. Again product is generated. The carry portion will be noted down. Here it is 7, and fractional portion is continued in the successive multiplication. Continue this process up to known number of significant position or required number of significant position, because this process will be indefinite. So if you want 4 number of significant digits, then only 4 step can be performed. If you want 5 digits after decimal point, then 5 successive multiplications can be performed, and so on. So we have noted the carry from the first multiplication, that is 4, and carry from the last multiplication, that is 3. The last carry will be noted as LSD and first carry digit will be noted as MSD as shown. And therefore, the decimal portion 0.6234 will be converted to the fractional part in octal as 0.47713. Now decimal to hexadecimal conversion. The fractional portion of hexadecimal fractional portion of decimal part is converted to the fractional portion of hexadecimal system. Again, logic is same. Whatever the fractional part given, that will be multiplied by the base of the system. The base of the system is, it is a hex system, therefore multiplied by 16. Then in the product, reminder, that is carry will be noted, and remainder will be, or fractional part will be taken in the next successive multiplication. Again, product will be generated. Here 15 will be carryover and 0.234 is the remainder portion, fractional part. This fractional part will be taken again and multiplied by 16 again. So you are getting the product 3.712. So 0.712 is the fractional part taken in the next successive multiplication, and the carry will be noted down. So continue this process up to the required number of significant digits required in the fractional portion. We have continued up to 6 digit and then we stop. Once the process is complete, the first reminder will be treated as MS digit and the last reminder will be treated as LS digit. So go on writing the digits from MSD to LSD from left to right after the decimal point as shown. So the number becomes 0.11 decimal equal to 0.1 F3B64H. This way, the hexadecimal conversion can be done. Now we will see the conversion of mixed decimal number to any radix. Mixed decimal number means what? The integer as well as fractional part is given and you have to convert it to other number system. For example, here decimal to binary conversion. Here decimal number given is 49.25. We need to convert it to the binary number. So what we do? We will take integer portion separate and fractional portion separately we are going to convert. The conversion logic for integer portion is we are successively dividing the number by the base of the system and remainder we are noting, and then taking the remainder from last remainder as MSB from bottom to top and the first remainder as LSB. Whereas in fractional portion, what we do? We will do the successive multiplication by the base to the fractional portion of the given number, that is decimal number, and note down the carry. Continue this successive multiplication up to the required number of significant digits in the required fraction of hexadecimal number or octal number or binary number. And then whatever the reminders we were getting, sorry, whatever the carry position we are noting down, we are writing it. The first carry will be MSB and the last carry will be LSB. So 49, we will see here, we will take the integer portion, 49 by 2. Quotient will be 24, remainder will be 1. Again 24 will be divided by 2. Quotient will be 12, remainder will be 0. 12 will be divided by 2. Quotient will be 6, remainder will be 0. 6 will be divided by 2. Quotient will be 3, remainder will be 0. 3 will be divided by 2. Quotient will be 1, remainder will be 0. 1 will be divided by 2. Quotient will be 0 and remainder will be 1, and the process stop here. So we are getting the column here. The last remainder is MSB and first remainder is LSB. So 49 decimal corresponds to, right from, start writing the MSB to LSB from left to right. So this is 100001. So here the first digit is MSB 10001. So the integer portion we have converted to the binary corresponding value. Here in step 3, you will see the fractional portion. What is the logic of converting the fractional portion to other number system? Take the fractional portion, multiply it by base, then the product will be generated. From that product, carry will be separated out and noted, and only remainder will be continued in the successive multiplication process. So here in the first step, the product is 0.25 into 2 is 0.5, carry is 0, we noted it, and 0.5 will be taken in the next step. Again multiplied by 2, you are getting 1.00. So carry is 1 and the fractional portion is 0, 0. 0, 0 will be multiplied by 2, process will be automatically stopped. So here you are getting the first carry, that is 0, that is MSB, and the last carry as LSB. Go on writing MSB on left hand side and LSB on right hand side. Now see the decimal point. From decimal point, the MSB will be first carry, that is 0, and the LSD, least significant digit, will be the next carry. So 0.01. 0.25 decimal corresponds to 0.01 binary. So therefore, the total number 49.25 decimal corresponds to 11001.01 binary. This type of examples may be asked in the examination for 5 to 6 marks. The another example, decimal to octal conversion. Now try it yourself. Let us see. We have the decimal portion, integer portion of the decimal number is 3000 and the integer portion is 0.45. As usual, we will take decimal separately, the integer portion separately and fractional part separately converted. So take the integer part of the decimal. We need to convert it to octal. So base of the system is 8. So successively divide the integer portion by 8. So here we are dividing the integer portion by 8 and successive quotient will be divided by 8 till the last quotient will be 0. And each step, whatever the remainder comes, we are noting down. The first remainder will be least significant digit and last remainder will be most significant digits. So we will write the digits from the remainder column from bottom to top, and therefore 3000 corresponds to 5670. So it is shown here. Now take the fractional part. In the fractional part, what we are doing? We are taking the fractional part and successively multiplying it by the base of the system, that is 8. So 0.45 into 8, that is 3.60. So carry will be noted as 3 and the fractional part remains 0.60. Take this second fractional part 0.60 multiplied by 8, it will be 4.80. 4 will be the carry and 0.80 will be the fractional part that is taken in the next successive multiplication step, and this will be continued up to the required number of digits. We have stopped this process after 4 steps, and we got here carry. The first carry will be most significant digits of the fractional portion, and the last carry will be the least significant digits of the portion, and therefore see the decimal point. After decimal point, MSD will be 3, so we have written 3, then 4, then 6, and then 3. So therefore 0.45 decimal is equivalent to 0.3463 in octal. Combining, last step will be combining decimal, this integer part and fractional part. So 3000.45 decimal will be 5670.3463 in octal. So this way you can convert the numbers from one system to another. In the same theme, we can convert decimal number to hexadecimal number. Again, if the number is given as a combination of integer value and the fractional value, then integer value and fractional value will be separately converted, and then the converted integer and fractional value will be combined. So here the decimal integer value given is 2003 and fractional value will be 0.31. As usual, we know in integer part conversion, we are successively dividing the number by the base of the system. We need to convert it to hex system, and therefore we successively divide it by 16 and noting the reminders. Every subsequent quotient will be again divided in the next step till the last quotient will be 0 and the remainder will be noted. Once the remainder is noted, we will write down the value of the remainder column from bottom to top. So bottom will be MSD and the first remainder will be LSD of the integer portion. So therefore, here 7, 13 corresponds to D in hex. So 7D3 will be the integer portion. In the fractional portion, the logic is again same. Fractional part is taken and multiplied by the base of the system, that is 16. Carry is noted down and fractional part is taken in continuation for next successive multiplication step. Go on doing this and noting the carry, and this can be continued up to required number of significant digits required. The first carry generated in the first multiplication is most significant digit of the fraction, and the last carry will be least significant digits of the fraction. So write MSD first after the decimal point, that is 4, say 0.4 here, then this 15 corresponds to F, so 4F, 5, 12 corresponds to C and 2. So 4F, 5C2 will be the fractional portion. Combine the integer portion and fractional portion now. So 2003.31 decimal is corresponds to 7D3.4F5C2 in hexadecimal. So we will stop here, friends, today. We will continue this unit in the next subsequent lecture. Till then, bye bye. Good day.